Good morning, everyone, and welcome to the Cryosphere Pavilion. My name is Ana Gomes, and I work as a researcher at CIMAR in Portugal with Arctic marine bacteria and their biogeochemical cycles. Today, I'm here to present our speaker, Dr. Gabrielle Kleber, and she's going to tell us more about glaciers and methane emissions. So, yeah.
Great, thanks, Anna. So I'm a postdoctoral researcher at the University of Tromsø in Norway, but the research that I'm presenting today is actually the research that I did during my PhD at the University of Cambridge, which I just finished up this past summer. So I'll start off going into just a bit of a background on methane. This is a topic that's becoming increasingly more prominent here in discussions at COP. Of course, the reasons for this, I don't really need to tell the people in this room, but I will touch on it anyways. Come on in. So methane is a really strong greenhouse gas. In fact, it's about 36 times stronger than carbon dioxide, and that means it traps a lot of heat in our atmosphere. It's already been responsible for about a quarter of the warming that we've already experienced. And that's going to increase. The atmospheric concentrations of methane due to anthropogenic emissions of the gas have increased to nearly triple the pre-industrial concentrations. And these concentrations are rising at alarming and increasing rates. But there are large uncertainties in the future of our methane projections, and that's actually due largely to natural emissions of methane. And that's because we have climate-sensitive systems that, as they warm, things like permafrost and wetlands, and as they get warmer, they start to release more and more methane. And so that makes it difficult for climate scientists to understand or predict future methane emissions. And what we call this mechanism is actually a positive feedback loop. And that's where we have climate-sensitive systems, they warm, they release more methane, and that in turn exacerbates or accelerates global warming. Now, the Arctic, as you can imagine, is particularly vulnerable to climate change. And making things worse, it's warming about 4 times faster than the rest of the world. And due to the fact that the Arctic relies on water being in a frozen state as ice, it has a lot of climate-sensitive systems like glaciers and permafrost and sea ice. And these systems are already seeing dramatic impacts due to a warming climate. Now, methane plays a large role in these feedback loops that we see in the Arctic, and that's because we have a very large reservoir of carbon, the building block of methane, stored within the Arctic. Now, I'm going to throw some large meaningless kind of numbers at you, but I will put them into context. So I'll tell you that we have about 1,300 petagrams of carbon stored within our permafrost. So that's the frozen soils that we have. And we have about 21,000 petagrams of carbon stored beneath our permafrost. That's in things like gas hydrates or oil and natural gas stored within rocks. But if I tell you that we have only 780 petagrams of carbon in our current atmosphere, you can see that just a release of just a small fraction of this carbon could have some quite large implications to our global climate. So this carbon right now is stored under and within something we call a cryospheric cap. And that's where we have glaciers and permafrost forming this kind of frozen barrier that prevents the release of this carbon. But of course, these systems are highly vulnerable to a warming climate. And so you can understand that as they degrade, as they thaw or melt, they threaten to release a lot of this carbon to the atmosphere. Permafrost, as I mentioned, is frozen soils, but as this soil thaws, it allows this carbon to become available to microbes. And they consume this carbon and turn it into methane. And so we have huge methane emissions from permafrost already, equivalent to the emissions that we see from the full country of Japan. So these are significant. And if we continue with the current emission rate that we're at, we can expect to see almost 0.3 degrees Celsius of warming by the end of the century just from permafrost. But if we move down to this sub-permafrost carbon, this is a lot trickier to understand. We know that the mechanisms exist for this sub-permafrost deep-seated methane to be released, but the timing and the magnitude is really uncertain. And so it's not well quantified, it's not well understood, and that means it's not really considered in our carbon budgets or our climate modeling. So we do already have some well-known mechanisms of methane release from these deep-seated methane reservoirs. One of those is high-latitude lakes. So we have lakes that are dotted throughout the regions of permafrost, particularly in places like Canada, Alaska, and the permafrost is thawing beneath these lakes, and that's allowing this deep geologic methane to be released. Right now, we're already seeing very large emissions from these lakes every year, and we expect those emissions to increase by more than 50% by the end of the century. We also have a really interesting phenomenon that we see particularly in the Russian Arctic, and this is something called a gas emission crater, and that's where we have methane gas build up beneath and within the permafrost, and it builds up so much pressure that eventually it kind of has this very catastrophic explosion, and it forms these large craters across the Russian landscape. And methane is released from these craters, and even after this blowout has happened, it has sustained emissions of methane for quite long periods of time. Additionally, we have submarine methane seeps. So this is where the permafrost at the seafloor is degrading due to warming seas, and that is allowing methane to vent up from the seafloor. We have mapped more than 7,000 of these seeps just in the Barents Sea, and we know that many more exist across the Arctic. So we are already aware that these methane emissions and the release of this huge reservoir of methane beneath the glaciers and the permafrost in the Arctic is already starting to seep out. But we don't really have a good idea of all the mechanisms. These are just a few of the mechanisms that we have already discovered. My team of researchers, we have discovered yet another mechanism, and that's in this paper that we published earlier this summer, and that's what I will take us through today. So we have found that methane is being released by groundwaters in glacial forefields. So basically this is groundwater that pops up in these regions where glaciers used to sit. So I'll go through just this kind of conceptual model to make it a little bit more clear. So we have this cryospheric cap that I mentioned. So that's where permafrost and glaciers create this frozen barrier. And that was back in kind of pre-industrial times when glaciers were big and healthy. And we had these groundwaters that were charged by subglacial melt, so melt at the bottom of the glacier. And methane was introduced to these groundwaters through the microbial production of methane, but also through the methane that's stored within the rocks, particularly rocks like shale and coal that have high levels of organic carbon and methane. But if we go to present day, where, as you can see from this fantastic rephotography that one of my colleagues has done on Svalbard, you can see that the glaciers have melted away and have left large areas of land exposed. And actually, this land that's exposed is not frozen. It exposes kind of this hole in this cryospheric cap. And that allows for these groundwaters, these methane-rich groundwaters, to come to the surface. And they bring this methane with it, and it's very quickly released to the atmosphere. But these groundwaters are able to flow year-round. Once they start flowing, they keep flowing. And so during the winter, they form these really large icings. We call them icings. It's where the groundwater comes to the surface and it begins freezing very quickly. And these icings can be several meters thick, and they can be several kilometers squared in area. So they're really large features in the Arctic landscape. So these are the systems that we've been studying, and we have focused on Svalbard. So all of our work has been up on Svalbard in the Arctic Norway. And now this area is really interesting, especially for these studies. Many people refer to Svalbard as the canary in the coal mine because it is warming extremely fast, actually 2 to 2 times faster than the rest of the Arctic. So it gives us a good glimpse into what we can expect to see across the Arctic in years to come. It's also an interesting place because it has lost a lot of its glaciers, especially in the last 80 years. We've seen a 30% decrease in volume of glaciers. So we've done our fieldwork up on Svalbard, as I mentioned, and our goal was to visit as many glaciers as we possibly could and sample these groundwater springs. So we based ourselves in Longyearbyen. That's the largest settlement on Svalbard. It has about 2,500 people on it, and it only has about 35 kilometers of road. And so that makes things very tricky for sampling glaciers. So we rely completely on snowmobiles and skis to get around to sample these glaciers. So we drive over the past 4 winters and springs that we have been doing this sampling. We have covered about 10,000 kilometers on snowmobile. So this has been quite a large project. But of course, not all days are blue skies and sunshine. We certainly face our challenges while doing work in the Arctic. We often have days where we are driving in complete whiteouts and you can see nothing ahead of you and you rely completely on a GPS to get around. We also deal often with very poor snow conditions where we get snowmobiles stuck far more often than we would like, spending many hours digging out snowmobile. We also deal with extremely cold temperatures. The coldest temperatures we had during our sampling was minus 42 degrees Celsius. And when we are trying to sample liquid water in these conditions, it's extremely difficult. It acts like super glue. And finally, what most people think of when they think of Svalbard are polar bears. And so we sometimes have our work delayed due to polar bears, but we certainly have this constant vigilance and this constant risk of having bears around while we do the work. But despite all that, we did manage to sample 123 springs in front of 78 different glaciers on Svalbard. So this region that we covered represents about 1/10 of the total area of Svalbard. So when we arrive at the glaciers, we find this icing that I described, and we drill into it with a drill. We drill until we reach this pressurized water, and we get a release of water in this kind of pressurized spring. And then we can take some measurements. If the conditions are not too terrible, we can take some measurements while we are in the field, but mostly we will collect the water in vials and bring it back for later analysis. So our results, of the 123 springs we sampled, all but one of them were super saturated with methane. Some of them were up to 600,000 times the atmospheric equilibrium concentration. That means that when this water reaches the surface and interacts with the atmosphere, it will immediately start releasing this methane to the atmosphere. So this is a significant amount of methane in these systems. And this graph or this map that I've shown you represents each spring with a bubble, and the size of the bubble represents the amount or the concentration of methane in the water. And if I put that onto a geological map of Svalbard, you see that these really large bubbles, so the high concentration springs, actually kind of congregate on certain geological units. And these units are typically associated with shale. So as I mentioned, shale has a lot of methane in it. So this implies to us that actually it confirms that the methane that we are finding is coming from this deep-seated, really large reservoir of methane. And we see that there is a statistical significance in the connection of the high concentration springs to this Jurassic and Triassic shales. So we are pretty confident that we are tapping into this large reservoir, and that is concerning because this reservoir is large enough that as long as we continue to allow the glaciers to retreat, we can assume that this methane will continue to be brought to the surface and certainly has the ability to increase its quantity of emissions. But we weren't surprised, actually, to find such high concentrations in these springs. And Amy's going to pull up a video for me. Come on in. We weren't surprised to find the high concentrations of methane in these springs because while we are out in the field work, we often bring a lighter so that we can kind of check the concentration of methane. And we find that the gases that are released from these springs are often ignitable. And so that implies that there's really high concentrations of methane in these gases and throughout these whole groundwater systems. Just get back to the presentation. Yeah, great. Okay, but what's really important in all of this is what are the actual emissions? So how much methane is actually being released from these springs across the Svalbard archipelago? So we were able to calculate an estimate of how much methane we believe is being released per year. And that is about 2.3 kilotons of methane. I know that's another kind of arbitrary number for you, but I'll put it into some context. It's equivalent to about 8% of Norway's annual oil and gas related emissions. For a more visual context, it's equal to almost 230 million party balloons being released, full of methane being released to the atmosphere. It's equivalent to the emissions from about 30,000 cows. And for a more local context, that's equal to about 65,000 camels. So these are not alarming emission rates. This is not something that is really making a huge impact into our total methane emission rates right now. But this is just from Svalbard. And we know that this reservoir of carbon extends throughout the Arctic. So we can certainly expect that these emissions are happening in places like Greenland and Arctic Canada, and certainly in Arctic Russia. So we know that this is not isolated to Svalbard. Also, we know that as glaciers retreat, we will see more and more of these springs. And so these emissions will continue to rise. And that is something we wanted to look into on our study. So we extended our study to look at a different type of glacier. So far, what I've discussed to you has just been looking at land terminating glaciers. And that means the glacier sits entirely on land. Its terminus ends on land. And that is different to a marine terminating glacier, which the large portion of the glacier sits on land, but it drains into the sea, and the terminus actually ends in the sea. And so we wanted to look at marine terminating glaciers and decide, are these going to be a future emission source for us? And so we had to look at about 3 different marine terminating glaciers. But I will go into the background with this little conceptual model. It's quite similar to the idea of the land terminating glacier. So you have this subglacial groundwater that's methane is being introduced to it by both the rocks and microbes producing methane, and it's being released in front of the glacier. When a glacier ends in the sea, this groundwater is being released into the fjord, into the water. And when it's in the water column, the methane gets consumed very quickly. And so you don't actually see much methane reaching the surface, and that really limits the amount of emissions that we see from these springs. But once the glacier melts enough and retreats far enough back that its terminus is now on land, it exposes land. And in that area, the groundwater springs can discharge. They can reach the surface, and this methane now has a terrestrial emission point. And what's important about this is that actually most of the ice that we have in the Arctic ends in the sea. So most glaciers that we have are marine terminating glaciers. And we're seeing that these are quickly retreating, and many already, 7% just in the last 2 decades, have already retreated onto land. So this is something we can certainly expect to see increase as our Arctic warms. So what we found when we visited these marine terminating glaciers was that we do find methane in the water there. So we took sampling on the sea ice. We drilled through the sea ice to reach the surface water beneath the ice in front of the glaciers. We did this in a large gridded pattern so we could get kind of a spatial understanding of where the methane is and how much methane is. And so we see that in front of all three of these glaciers that we do have hotspots of methane in front of the glaciers. So we are quite confident that these groundwater springs are active in these kind of subsea forefields, these areas in front of the glacier in the fjord, and that once these glaciers retreat onto land, that we will see these terrestrial methane seepage points. So of course the question is, do we need to worry about this? And I would say yes. I think we need to worry because these emissions are out of our direct control. Once this mechanism has been initiated, which very clearly it has, we cannot stop it or reverse it. We can only slow down the increase of these emissions by drastically cutting the emissions that we can control. We should worry that there is a massive geologic reservoir of carbon in the Arctic. And this is ancient methane that's been stored in the rocks for millions of years, and we're allowing it to be released to our atmosphere. And we don't have control over the rate at which it's being released. And this reservoir extends throughout the Arctic. So we know that these emissions are possible across the Arctic. We should worry that glacier melts is accelerating. And so we'll see more and more of these springs pop up as we allow more land to be exposed by melting glaciers, and more marine terminating glaciers turn into land terminating glaciers. We should worry that despite all of this, we are still approving new licenses for fossil fuel drilling in the North Sea. We just approved 27 new licenses last month. We should worry that despite all of this, we are still subsidizing the oil industry at record rates. We subsidized a record-breaking $7 trillion just last year. And we should worry that we are still questioning the 1.5 degree threshold when the science is very clear. We need to aim for well below that. And I will end with a sentiment that has been repeated by my colleagues many times at this COP, which is we cannot negotiate with the melting point of ice. Thank you. Any questions?
Yeah, so you get this point measurements, how do you upscale them? Just measure one point, each of these locations.
You mean like how do we get from the concentration to the flux measurement or the total amount?
The entire swallow.
Yeah, so we use the volume of the icing that's created during winter, and use that volume multiplied. A basic description, the volume of the icing multiplied by the concentration of methane in the spring to estimate the year-round releases from each of the glaciers. And then we simply expanded that across the rest of Svalbard because we managed to cover nearly every glacier within this 6,300 kilometers squared area of Svalbard, which represents about 10% of the island. So we extrapolated that.
So you assume essentially one point measurement becomes across the entire area they consider.
Well, these springs are isolated. So we have, it's just one spring that we're able to sample. So in front of a glacier, we may have multiple springs, but we sample all of these springs that we find. And so we have a different level of methane at each of these springs. So it's 123 point measurements essentially that we have then extrapolated across Svalbard. Any other questions? Great, thank you.